Okay, so with luck, people are able to hear me at this point. So I'm going to just quickly check. Saves the video. That's not great. Give me one moment. Let me try improving video quality here. Okay, that looks marginally better, so let's give this a go. Great, so my name is Matthew Garrett. I guess I do computers. One of the things that I have an interest in is the interaction between the hardware and the operating system, the layer that is to a large extent mediated by the device firmware. Now, you're probably all aware of this, but the firmware is the code that's responsible for initializing the system hardware and getting us into a state where an operating system can be loaded and executed. There's some extent to which the firmware is also going to be used at runtime. I'm largely going to ignore that for the moment, and instead we're going to focus on getting firmware we control into a state where it can initialize the hardware. So there's two components of what I'm going to be looking at today. One is the hardware that I'm talking about. The machine that I'm going to be attempting to work with today is... okay. Audio has some jitter. Let me see what I can do here. It should only be taking audio from a single source, but I am not a professional in this respect. Oh, right, sorry, I see the problem. Okay, is that better? So it turns out it was me capturing audio from more than source. How are things? Is this any better, or have I completely misidentified? Okay, double quickly. Let me try just dialing the volume here. Okay, how is this? You take for granted when the platform just takes care of everything for you without needing to care about details. Apologies, this is all novel to me. I don't fundamentally understand why it is using this tool. turning the volume up again. Right, how are we doing now? Amazing that audio is not a solved problem. Okay, there's a bunch of stuff that, right. Okay, so we are now down to there only being a single audio input, so that should, in theory, be better. It seems to be responding to my voice, so I assume it's actually recording. One possibility is that I am just running out of CPU. Give me a second. Let me just change the video quality again, and we'll see whether things get better. Okay, so of course you say it's absolutely perfect the moment I start killing the stream again. Right, let's take that from the top. My name is Matthew Garrett. I am going to attempt to port Coreboot to a Framework laptop. For those of you who are unfamiliar with either of these things, I'm a little confused what you're doing here, but let's see what we can manage. The Framework is a laptop produced by, let me show you their website. These people. It is a laptop. It is designed to be straightforward to disassemble. It comes with little plug-in modular components that allow you to expose different physical ports on the side of it. Every component is labeled internally. It is designed to be easy to disassemble, to replace parts. It's supposed to be maintainable. In principle, you may be able to upgrade aspects of it without having to replace the entire machine. So obviously, there's a degree of overlap between the number of people who are interested in machines where they have a reasonable degree of control over the hardware and the repairability of it, and people who would like control over the firmware that's running on the system. Now, unfortunately, the Framework laptops that you can currently buy make use of something called Intel BootGuard, which is a technology that ensures that the firmware that's running on the system is accompanied with a valid signature controlled and a signing key from a signing key that is controlled by the manufacturers of the laptop. And that means that it's not possible in a straightforward way to simply replace the firmware on the device. Now, Framework have been kind enough to send me a machine that has not had the the public key programmed into it, and as a result will run any firmware that I intend to install on it. And there are a couple of mechanisms that I'll go into later if we actually have any degree of success here that would potentially allow for Coreboot to be ported to machines even with the BootGuard feature enabled. Now, that's going to be something that's going to require the cooperation of the hardware vendor in question. I'm not saying that this is a scenario where, based on any of this work, you're going to be able to suddenly install Coreboot on a random laptop with BootGuard enabled. Coreboot is an open source firmware implementation. It's intended to handle the low-level initialization of hardware and get you to the point where you can run what Coreboot refers to as a payload. A payload might be something like CBIOS, an implementation of the legacy PC BIOS interface. It might be a port of the EDK2 EFI development kit implementation, which allows you to run a UEFI-based firmware. Or alternatively, Coreboot can be used to just chain into Linux directly, skipping the firmware interface that's normally exposed. So what I'm going to attempt to do today, and almost certainly fail at, is get to a point where Coreboot is running at least one payload on this machine. Now, I'm not going to be starting from scratch here. Another vendor, System76, already produces laptops based on the same CPU family as this framework. And the largest part of the work is basically handling that integration. So because I am fundamentally lazy and because I also don't have a particularly good idea what I'm doing, I'm going to just go from the implementation that already exists, attempt to make use of that, and then see whether just basically filing off the serial numbers and putting new ones on results in the system becoming functional. So that's the brief introduction. Here you can see that I have an SSH terminal onto the framework machine, which is sitting next to me. Here I have a checkout of System76's firmware build chain. So I'm going to first of all attempt to identify a System76 laptop that is based on the appropriate architecture. We're talking about Intel's Tiger Lake architecture, which is their mobile architecture for 11th generation core-based CPUs. And we can see here that we have a few different machines. So what's notable is the PCH-H. That's Intel's higher end, more power-hungry mobile CPU architecture. So we don't want any of the PCH-H ones. We instead want to be focusing on one that just does this. So let me just look at System76's website quickly, and we'll just pick whichever one of these seems like the closest. No particular reason other than, the more similar they are, the easier potentially. So looks like we have the choice of the Data Pro, which is a 15-inch system. The Galago Pro, which is a 14-inch, or the Lemur Pro, which is also a 14-inch. Of these, but the Lemur Pro looks like it's probably the closest, so we'll start with that. So let's open another terminal. And I just realized I have no idea what the model name of this machine is. So let's look at that, and we discover that it is apparently simply called laptop. Okay, that's not super helpful, but laptop. And there we go. Coreboot is now ported to, no, obviously. It turns out we have some additional stuff that we need to do, like what is any of this stuff that is in this hardware-specific directory? And the answer is a bunch of hardware-specific stuff, shockingly enough. So let's look at these one by one. The first I'm going to look at is this data.vbt. Now, the VBT is information that Intel's video driver uses to it provides information about what the hardware is capable of to the video driver, not just the runtime driver, but also the driver that's initialized in the firmware. So we're going to need a copy of the VBT from the framework device to replace that with. And thankfully, this is fairly straightforward. Or is it in debugfs? Yeah, it's here, isn't it? Right, i915 VBT. Cool, that looks legitimate. Okay, so we have now provided information about the framework's video stuff and copy that in here instead. All right, now what? Oh yeah, we should probably edit this stuff. So it is not an SOIC. I can't remember the packaging name. It's the slightly flatter one. Anyway, come back to that later. So okay, let's look now at the setup of the audio hardware. This is also available so, okay, first of all, it's a 295, not a 293. Now, the pin information. One of those things where I should probably just have actually done my research before starting this. 1 second. Oh, right, yes, I'm looking at the wrong thing. There we go. That's better. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool. Okay. Well, that's convenient. That's the same. That's the same. That's the same. That's not present. 12, 13, 14, 16, 4, 0, 16. So these are effectively bits of configuration data that define how the audio codec is configured, which is something that can vary between boards based on different audio speakers being connected to different pins, microphones being connected to different pins, different types of configuration. None of this information is particularly exciting, but it does need to be correct if audio is going to work properly. So I'm just extracting this information that the kernel is already familiar with. 12, 13, 14, 16, 17, 18, 19, 1A, 1B, 1D, 1E. Okay, cool. And in principle, we have now ported everything we need for the audio configuration. Basically, we're finding all the components that are board specific, and we're trying to move those into, we're trying to extract the information that has been programmed by the existing proprietary firmware, extract that information and provide that to Coreboot so that Coreboot can make use of the same data. Okay, let's see what else. So there's various bits of CMOS config which are going to be which record state. Let's just not worry about that. If I wanted compatibility with the proprietary firmware, then that would be something I'd need to continue caring about. But at the moment, I basically don't. So let's see what we can get away with. So far, so straightforward. But what about this GPIO? Here is a lot of very board-specific stuff. This looks concerning. So there's a whole bunch of logic on the board on modern mobile parts that is a bunch of pins on the chipset can be configured for different purposes, and we need to configure them equivalently to the way that the proprietary firmware has configured them. Otherwise, we're probably going to have a bad time. This is stuff like just how various hardware components are hooked up to the chipset. If these are not equivalent, then we expect that stuff won't work properly. So here's an example. What we're looking at here is still the GPIO configuration for the lemur, and it's defining the pin on the chipset that the touchpad is connected to, and there's no reason to believe that the configuration on the board that I'm working with is equivalent to this. So we're going to need to attempt to extract the information about the running system and configure the GPIOs that way rather than configure them the way they are for the lemur. Thankfully, there is a tool for this. So let's build this. And then let's run that. And okay, that's not super positive. There's a whole bunch of unknowns. But let's ask it to give us the GPIOs, and okay, we are not getting the GPIOs, denied. The tool that is capable of reading the information from the running chipset is not capable of understanding the it doesn't know which chip it's talking to, and it doesn't know the registers that the GPIO data is kept at. It has no ability to provide us with this information. So we're going to need to work on this a little. So let's start by looking for that error. Okay, convenient enough. So we see there's a big list of PCI device IDs, and yeah, ours is not one of them. So let's start by just figuring out where these PCI device IDs are kept. Thanks, crap. Okay. And then let's look at Alice PCI. So the component we're looking for is the south bridge, so it's A082. So 1F0. Okay. So the naming that I'm going to use here is not going to be correct, but I'm more interested in just making this work than I am anything else. A082. And we're just going to tell it, okay, if it's running on the chipset associated with the Tiger Lake CPU, then treat it the same way that you would treat any other recent modern Intel chipset. Well, okay, that no longer gave me an error, but it didn't actually do anything. So let's see. So it was calling print GPIO groups, so that code lives in here. And so it calls get GPIO communities, and if it gets that, then it prints this. We never see that being printed, so that means that it's following this code path, and so we need to figure out what this does. And we see another case of, right, it varies depending on what is there. So we see that there are different sets of these for each chipset family. So this is a case where we should probably not assume that the chipset, this more modern chipset, behaves the same way as any of the existing chipsets. So where are these defined? In GPIO names, okay. And right. Okay, there's a lot of stuff here. So we have multiple different communities. Each community contains a bunch of groups, and then each of these groups has various names associated with it. So now we want to try to find out where that information came from. Okay, so apparently the GPIO information comes from the chipset documentation. Let's see if we can pin that down any closer. Not really. Okay, so what was this Intel doc? So 337867 is the Intel document number for the volume 1 of the 300 series chipset on package PCH datasheet. I have considerately downloaded those beforehand. And okay, what we see here is that the chipset document has an embedded Excel spreadsheet. Awesome. We'll wait for LibreOffice to figure out exactly what it's doing, and then with luck, we'll be able to see some evidence of that at some point. Okay. GPIO implementation. Woo. So, right, we get a bunch of information here about each GPIO. Has the GPIO name, blah, and then tells us what the native function is. So this is information about native functions are things where you can configure the GPIO to be attached to a specific piece of functionality within the chipset. So that's then, in this case, should this pin be configured such that it is going to, if triggered, cause the USB overcurrent thing to be indicated. But it could instead be programmed to perform one of these other functions instead. And it looks like we have 7 possible functions. Yeah. Whereas the... So we have the... if we go back to looking at, you can go away now, this, we only have 4. So boop, boop, boop. Okay, I'm going to go for the straightforward so did that do the right thing? No, it exports this as HTML. Okay, let me try that again. Oh, I see. I don't want exports, I want save. yes, I am extremely aware that it is going to contain information that is not exportable in this form. Right, let's put you out of the way again, and okay, much better. So what we're going to end up wanting is a series of structured definitions that contain each name and each use. This is going to be tedious. So everything we care about starts with GPP, so let's go with, we're going to start from that. Excellent. Then let's go with, this is absolutely the worst way to deal with CSV, by the way. You should not attempt to just use awk to parse a CSV file. That's generally going to result in unhappiness, but anyway, here I go. Sorry, no, two. Really? Okay, apparently I just don't know how to use computers. It's a common problem. I'm sure you're not actually here to watch me flail at this, so give me one moment. Basically, I need to cut and paste the data from these this spreadsheet into a file that looks like this, so the Intel tool will then work. But that seems like a really annoying thing to do. So here's one I made earlier. Sorry, I'm cheating. So I actually did go through some of that process earlier, but really wanted to walk through that. So there's no magic involved here. I've shown you the data that I would be extracting. I've shown you the format I would need to extract it in. And look, here's a file that contains it. So let's copy that here. Let's figure out did I just call that file? I'm so bad at this. So we do still have one question here, which is what is the pad stepping? Pad stepping here refers to the how many bytes, sorry, how many registers should we increment when looking at the GPIO data? And the answer to that is something that we'll need to check the docs for again. So give me 1 second and I'll find the right doc for that. So this is not what we're looking for, but this is going to come in useful later. Okay, so I think it's in volume 2. No, that's not it. This is ACPI related stuff. Oh, here we are. Right, yes, this is absolutely fine. So each pad, so each basically GPIO register is configured using 2 different things, DW0 and DW1. And as we can see, the offset between the one for H15 and H16 is OX10 or 16. So we can go back here and we can go with okay, maybe this will build. It did. Maybe it will run this time. Place bets now. That is my favorite output. Unknown LPC device success. So going to go with that's coming from PCR init, right? Okay, so it is going to speak to the chipset. We're probably going to be around here. Let's just YOLO this. And we reach a mild impasse in that I forgot to... So the /dev/mem interface is a piece of kernel functionality that allows you to read from arbitrary address spaces inside the physical memory address range, which may not be... The name's confusing. In this case, we're not actually trying to allocate access memory. We're trying to access registers that belong to the motherboard chipset, but which are mapped into the physical address space in the same way that memory is. The kernel decides, for the most part, that it's probably not a good idea to allow userland to access address space that belongs to a piece of hardware on the assumption that if you poke it, the hardware will probably do something confusing unless you really know what you're doing. So by default, the kernel blocks that access. So I'm going to have to reboot this machine and tell it to be less restrictive in that respect. So give me one moment. Let me just get into grub here, which I just failed to do. Let me reboot that again. So I'm just in grub, which you can't see at the moment. And I'm just adding the IO mem equals relaxed arguments to the kernel, which will tell the kernel to allow me to access address ranges, even if they are allocated to IO devices. We'll wait for it to boot, wait for it to get online. Okay. Success! We have a bunch of GPIO data. So let's put that somewhere. IOMEM equals relaxed. Yes, that is correct. I've lost track of where I was keeping this. Let's put it here for now. So, we have GPIOs, but at the moment we just have, the actual value of the configuration registers for each of them. We don't have that in the format that we're going to need. So let me remind you what that looks like. oh right, it looks like this. And this is the raw register value. We need something that's able to take this and turn it back into this. Now, thankfully, there is such a thing already. If I can just remember what it is called. And this is written in Go, which is, you know, the worst way of trying to remember something. Oh, that's it. Intel P2M. Which is a tool to convert the configuration DW0/1 register values from Intel tool dumps to Coreboot macros. So let's build that. Thankfully, I have a Go toolchain installed. And then what's it tell me to do? Run tell pin to macro as file /tom/firmware GPIOs. And well, it did a thing. Now, something that we probably want to check here is, well, was that exactly what we wanted? And right, it turns out that by default it assumes that we are on a Sunrise Point chipset, which is not what we are. We are on a Tiger Lake SoC. So we probably want to look at which. So this is probably a case where we're going to need to add code again. So this is a case where we need to add support for parsing out what the individual bits in the DW0 and DW1 fields mean, and potentially adding support for that. So let's grab that spec again. And let's see if we can find where DW0 and DW1 are described. Cool. It's just a reference to look at this other one. Apologies, this is not the most thrilling content right now. Yes, I think you're just showing. Right, okay, here we go. So this is possibly relevant, this information here. So different chips apparently, different communities potentially have different default values after reset. So that influences whether or not we actually need to do anything there. Okay, so what I'm going to say is, first of all, let's go back and figure out how to there, right, okay, so config.canon time, okay, let's find the references. Okay, so far so, wait, hang on, right, yes, I'm going to need to add it to this. Okay, add that there, and then, does this get used anywhere here? Yep, it does, so let's duplicate that. Cool, okay, that was straightforward enough. Main.go. Right, that looks straightforward enough. With luck, that's enough to get it to actually care about anything that we have given it. But then we're going to need to update this. So we're going to need to add a new parser there. I have no real idea what I'm doing here, by the way. I'm just assuming that if I cut and paste enough stuff, magic will happen, which may or may not be accurate, you know. Okay, so let's then go to platforms. Let's copy that. Let's replace that, and then let us think about what we're going to do next. So we're going to need to rewrite the parser here, rewrite the platform data here so that it corresponds to what is defined in the Tiger Lake docs rather than the kind of like behavior. So let's work on the assumption to begin with that with luck most of these are pretty similar. So we've got read-only fields, and so read-only fields in Cannon Lake were apparently bit 27, bit 24, bits 21 and 22, a whole bunch of bits around 16, and a bunch of stuff at the bottom of the range. So which of these are read-only? Bit 27, you can see here, is marked as read-only, so that's good. Bit 24 is read-write, so we probably want to get rid of that assertion. Bits 18, 17, and 13 through. So everything from 13 up to 18 is read-only. Well, that's a bunch of things. Let me try to 13, 14, 15, 16, 17, 18. That's 6 bits. That's 2F. 21 was not, so does that seem right? So that was 1, that'd be 13, 2, 14, 4, 15, 8, 16, F 17. No. Yeah, okay. I think 2F is correct. Really looking out for you in chat to correct me on this, otherwise potentially RIP absolutely everything. What else is read-only? It's 7 through, bits 1 through 7, so that should then be FE. Plausible. Okay, sure. Let's work on the assumption that I know how to do this sort of stuff in my head. It's probably a complete lie. Okay, I'm going to cheat here. Binary. GNOME Calculator is shockingly useful for this sort of thing. So DW1, bits 0 through 7 are read-only, so that's 0, 1, 2, 3, 4, 5, 6, 7. No, wait, that's going to work badly. So 31 to 14 are read-only. 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Which gives me FFFF C3 FFFF. Haha. Right, that was a bunch easier. Yeah, I should probably actually just go with, let's do the same here. I do not trust my ability to do this whatsoever. So 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. That's 31, 30, 29, 28, 27. Yeah, okay. And that is that. So oh, right, leaving 0. Okay, now that's the right length. Awesome. So what's this stuff about? Reset maps. So let's look at okay, so there's the default map, and then there's the COM0 map. Okay. So community 0 has a different reset mapping, as is described here. Whereas on Tiger Lake, it seems to be community 2 that has so what's in community 2? So this is information that we get from that spreadsheet that I was looking at previously, a mixture of that and the docs. And it looks like that is just a single set of GPIOs, in this case called GPD. Okay, so maybe that we're getting there. We're making some progress here now. Oops, sorry, wrong button. So these seem to be making the assumption that the 0, the 0, 1, and 2 are related to the reset behavior. Okay, so what we see here is that RST config shift is looking at bits 30 and 31. 0, there is RSMRST, which corresponds to what we have in the chipset docs for this specific chipset. 1 is deep. Yep, looks good. 2 is PLT RST. That also looks good. So let's assume that that's correct and we don't need to modify it in any way. Okay, so it has reset config. Then we're going to look at the termination parameters from a DW1. And so, same way, So here we have 0. Here corresponds to none, and then this is I can count, I promise. So, right, 1, 2, 4. 4 is 20K. That looks equivalent. For 12, OXC is up, pull up 20K, yeah, and then all else is native. So those are consistent. In principle, that means that these other values are probably not permitted. I'm going to just leave them in because we're going to be reading from the configuration that already exists on the machine. And so if they're programmed in a specific way, then I'm going to assume that's correct regardless of what the chipset docs say. It's just trying to turn those into useful macros. Okay, so that seems to be everything in here. So the rest of this is just comparing what's in the 500 series dock to what's in the 400 series dock and making sure that they match. I'm going to go with it's probably fine. These things don't change a lot. If we end up with garbage, then I'll revisit that. But for now, sure, let's go with that. And then let's take a look at the template. And we've got a bunch of group names. The group names are different between the two between Tiger Lake and Cannon Lake. So just going off my notes from earlier, we can. This is basically again information that was from the spreadsheet. I'm just going to fill these in. So this is just basically listing these sets of GPIO groups that exist on the platform. There's nothing particularly magical about these names. It's just basically going through the list of GPIO groups that exists in the 500 series document and making sure that they're all present here. So does this build? No. IR professional programmer. Oh yeah. That's probably going to work better. Cool, okay. So minus p tgl minus file slash template firmware GPIOs. And okay, there we go. We have a big list of GPIOs and their configuration. May or may not be correct. Who has any insight into that whatsoever? You know, other than people who are paying attention to what machines actually do. Whoops, sorry about that. Just delete all this. Okay, so that's the GPIO configuration done. Okay, so here we have something that does early configuration of GPIOs before the main setup code, as it's called, and it looks like this is so that a serial port can be hooked up to a specific set of GPIO pins. So that's be for debug purposes. I have no idea whether this exists here, so I'm just going to get rid of that. And delete that. Okay. Let's look at bootblock.c. Okay, so I want to get rid of that as well. Anything concerning here? Nope, that looks fine. Runstage.c. Yeah, so this is setting up the addresses where it should look for memory. This is checking. So it's going to scan an SM bus, which is a sort of not quite a smart I2C bus, in order to look for DIMMs that are present and then query them. It looks like this setup is for a single DIMM machine. The framework's actually let me just pull the cover off and take a look. Yeah, appears to be a dual DIMM machine. So we're going to want to change this to look for both slots. And again, the easiest way of doing this is just go for let's look at an example of one that has two addresses here, and it's apparently just so the first DIMM slot is basically always at address 0x50, while the second one's at 0x52. So now, oh right, and the other thing is that there's no on-board memory, so let's tell it that the topology is that it's all DIMM based. But should be DER4. Okay, so that's now got us to the point where we've fixed up the majority of the board-specific data that exists here. But that doesn't deal with ACPI. ACPI is a specification for a mechanism for the firmware to pass information to the host operating system, both about static data, but also as an abstraction mechanism for communicating with various bits of board-specific circuitry. So as an example, Linux running on those PCs has no way of knowing how to speak to the battery recharge circuitry directly. Instead, ACPI provides a method for Linux to execute, which then reads a bunch of registers from various places, does some things, passes the information back. So ACPI is extremely board specific. It's a mixture of information not just about the board, but also what the operating system expects. So I'm just going to go ahead and get rid of temporary backup files I've created. And then let's look at what the main board is. So we're seeing that it's pulling in a lot of generic stuff. And then so this is information that is going to be present on basically all boards with this chipset. And it's also including down at the bottom some motherboard-specific data, which includes some information about sleep, which includes information about the embedded controller, includes information about the backlight. This is stuff that is going to be important once we get to the point of there being an operating system running. But for now, we can just lose that. Is this SPD data being included anywhere? Nope. Okay, so let's get rid of that SPD directory. And we removed the reference to configure early GPIOs. Okay, that is in principle enough code that we should have something running, but there's a bunch of additional stuff that we need before we can actually build something. One of the big problems that we're going to face is that there's a bunch of additional binary data that is used in building this. And we're going to need to obtain copies of all of these blobs, basically bits of data that will be required for the system to run, but which Coreboot, which is sufficiently system specific that Coreboot doesn't know about them. So where are they putting them? I see, they're in here. So I'm just going to do this. And then, well, no, we were basing off the Lima Pro 10. Bunch of weird stuff here. Oh, so some of this is right, the stuff that we generated. So if we want the, so the FD is the Intel flash descriptor. It's a basically header for the ROM that tells it how to do useful stuff. Or it tells it what the layout of the flash chip is. So what we can do is lose these bits. The GOP driver is probably going to be the same for these, so we'll make use of that. The microcode is probably going to be the same. USB 4 stuff may or may not be the same. I don't know. We'll leave it there for the moment. BBT we've updated, so we just need the me.rom and the fd.rom. The me... Wait, what? Oh no! Why have you got to do that? I'm just going to drop binaries in here instead. So we're going to need a copy of the system ROM in order to be able to extract this information. So how up to date are we? Let's maybe not use a version of Flash ROM from 3 years ago. Let's build this. Flash ROM's a utility that can be used to communicate with various bits of Flash hardware, and it supports using the motherboard controller to read and write Flash. So let's go with all right, it needs to tell it what to use. -p into kernel. Okay, there we go. It is now reading the Flash from the framework system. And then we'll copy this over and try to extract the information we need from it. Ooh, 32 megs of Flash. That's a lot of Flash. So one point of detail here. Laptops generally contain an embedded controller, a separate chip running its own firmware, which is responsible for various housekeeping tasks. It's usually the thing that drives things like the battery controller. It's the thing that is awake enough for your laptop to wake up when you hit the power button, even though the main CPU is not running. The firmware for that can be stored in various places on different boards. So my first attempt to port Coreboot to the X210 weird Chinese ThinkPad device involved me producing a firmware image that contained no embedded controller firmware, and then the embedded controller firmware failing to boot and the system not working at all. I took a quick look at the contents of the framework's Flash and found that there is a copy of the embedded controller firmware in there. So my concern was that the embedded controller needs to read the firmware from the system Flash. I checked with Framework before starting on this today, and they said that while there is a copy in Flash, that's not what the embedded controller actually uses. The embedded controller is getting its firmware, it is storing its firmware locally. So I'm not going to worry too much about attempting to ensure that there's a copy of the embedded controller firmware inside the Flash. By the way, something I should have made clear at the beginning is that what I'm doing right now is very much just the bare minimum to get a board up and running. When, if this works, which is very much not guaranteed, we're going to have something that does not have any sort of particularly coherent support story around it. We're going to have a firmware image that is capable of booting the system, but it's not going to have a mechanism for, say, updating the embedded controller firmware. It's not going to have a particularly good story about providing system-wide firmware updates. Right now, the fact I'm skipping all the ACPI stuff means that there's not going to be any way for the platform to actually communicate with the underlying device-specific hardware in any useful way. Getting Coreboot up and running on the platform is very different to Coreboot being a meaningful firmware implementation for that platform. And I just don't want anybody to end up with the impression that if by some miracle this does end up working now, that this is equivalent to actually building something that is sufficient for an actual product to make use of. Anyway, let's reuse this window. And let's copy that file over the network. And then we're going to go back to here. We're going to lose track of what we were doing, and we're going to build IFD tool. IFD tool is a tool for manipulating the flash descriptor, the header file for the flash that I described earlier. And we're going to tell it to, oh, it supports Tiger Lake already. That is convenient. And we're apparently supposed to tell us do something, specify a mode. Let's go with MySC. And that dumps a bunch of information. Oh, lots of information. So there's a bunch of bits in the header you can set that cause the chipset to change its behavior. We're going to just assume that they are all set reasonably. And let's extract stuff. Okay. So this looks reasonably promising. So we have a blob that corresponds to the BIOS. That's going to be the platform provided stuff. There's a blob that corresponds to the Intel management engine. The management engine is a component in the chipset that is running its own independent CPU, effectively. It executes code, it is able to do a whole bunch of platform management functions. It's sort of intimately involved in the CPU being powered up in utterly terrifying ways. It's running in the background. We have no particularly good insight into what it's doing. Kind of terrifying, really. And it needs its own firmware, which is stored in the system flash. So we need to extract the management engine firmware for this device and then make this available. What is a bit concerning here is that the management engine stores its own configuration data inside its flash region, which can include stuff that is very intimately tied to the specific machine. So the blob that I'm extracting now is associated with the specific laptop, as opposed to it being one that is unconfigured. And so while extracting this and then incorporating it into Coreboot may well work, it's not an ideal scenario. Really, Intel has some tooling you can use to strip that configuration data, but it's something you need to take into account. If you extract the NE data from a specific machine, you should not put that into a Coreboot build that you're planning to distribute widely, because it may not work correctly with everyone else's machine. So we've got the flash descriptor, we've got the Intel ME. Let's copy this to okay, and then we're going to copy the it would be good if I could type consistently. Right. So at this point, we nominally have a configured system, but there's still something important, which is this device tree file, which contains the information about the explicit configuration of. So this is basically a configuration file that tells Coreboot and other components how to configure this specific machine. Now, something that I failed to mention earlier is the existence of something called the FSP, the Firmware Services Package, something like that. Coreboot is an open source free software code base, but unfortunately Intel does not describe how to perform full hardware bring-up of any of their recent chipsets. And that means that Coreboot relies on a lump of binary code that Intel provides called the FSP. And the FSP is effectively a blob. You pass some configuration into it, and then it returns, and now the hardware works. This is obviously not how we like doing things in the free software world, but things like memory controller configuration in the modern DDR world are sufficiently complicated that reverse engineering this, implementing a completely open version of this, is incredibly difficult. Especially when we've got roughly a year between implementing something, between a platform launching, us attempting to, when I say us, I mean I have not actually tried to do this myself, people attempting to reverse it, and then a year after that, a new chipset comes out with a new version of, with a new set of requirements. I should probably try to make sure that at least the power, so Intel has support for controlling the power limits on their chips. PL power limit. A chip should not be able to run sufficiently hot that it's able to overheat, cause damage to the system. And some of that is controlled by the power limit variables. So you want to have the device set up so that this is a case where the PL values for a chip are influenced not only by the chip itself, but the entire physical object that that chip is embedded within. The ability to dissipate heat needs to be equivalent to its ability to generate heat. Otherwise, you're going to end up with a system that will eventually melt or set fire to people's trousers or something like that. So you can't infer the correct values for this based on what the chip's behavior. You need to infer this from the entire platform design. PL1 and PL2, PL2 is the power limit that it can burst up to for short periods of time. PL1 is then the sustained power limits. The idea is that it's okay to consume a higher amount of power for a short period of time because that will not end up generating a huge amount of additional heat. But if you're still trying to run at high speed, less than that, then you're going to end up dropping the power limit and dropping probably the CPU frequency as a result. This information is available through sysfs. So here we're going to look at the package limits. So what is PL2 set to? That's kind of a lot. Wow, really? One, two, three, four, five, six. That is 6 zeros, right? Yeah, okay. Well, if they say that it can withstand yeah, okay. If they assert that it's able to deal with that's also higher than I expected. Sure, whatever. If this is the it's possible that I've gotten off by 1 here. And yeah, I think actually it's that Linux refers to these as 0, 1, and 2, and Coreboot refers to them as 1, 2, and 3. Let's see what that looks like. Yeah, okay. That's still a higher PL2 than I expected, but sure, fine. We'll oh, what? I apparently still can't count, and that is 200. What I'm going to go with here is that this is a pre-production device running pre-production firmware, and it's possible that these values are complete lies. So, realistically, I'm just going to leave these at nice, safe values. So there's a bunch of configuration here which is passed to the FSP. I don't have access to sufficiently good docs to be able to figure out how much of this is See, I don't even know what FIVR is. Okay, there's a bunch of stuff here that I would have concerns about and which I should really configure appropriately. It's probably fine. It's probably fine. I'm going to get rid of this GPIO config because oops. I don't trust that it's actually relevant to what I'm doing here. And System 76 people do have the benefit of knowing how their hardware actually wires up. To that credit, Framework people have offered me access to some internal information that would make it easier to figure out how everything here should be configured. I've chosen not to make use of that for this stage of things because I don't want to have to repeatedly look at documents that I'm not allowed to tell you anything about. What's going on here in this section is just information about the configuration of the different USB ports, whether they should be enabled or not, and also the type of cable that should be connected to them. All the external USB ports on the framework are USB-C, but let's also go with that was not as useful as I was hoping it would be. Okay, I'm going to come back to this. If we're at the point where the system is even able to talk to USB, we'll be in a much better place than I expected that we would be. Yeah, okay. Going to get rid of that. Are we using ICC? Yeah, okay, there. So this is also bad. I really need to configure the I2C bus so that the platform is, so the operating system can actually extract information. Some of this is also going to have to be added to ACPI. So again, I'm going to delete a bunch of this. This is very definitely information that has to be added at some point. Serializing, okay. Like I said, right now what I'm doing is, can this machine boot Coreboot? We are a very, very long way from saying that this is a fully functioning port, even if it does. So which PCIe root ports are enabled? 0, 1, 2, and 3. Which I think in whoops. Yeah, so most of this config is, my recollection is that it's 1 indexed, whereas everything else is 0 indexed. This is information about various things that should go through I/O port decoding. That may or may not be correct. Yeah, let's get rid of this as well. Okay, let's leave the PS2 keyboard controller there. So a bunch of this information is probably not correct, but is at this point probably not enough to prevent the system from booting. So wait, that's not right, is it? 16384 times 2 into 7. 277, 384. Yeah, 768. It does have I2C hid, but right, we're going to disable this. Disable that. Right. So at this point, just trying to hook up all the configuration stuff so that the build system will actually attempt to build stuff. I'm leaving out, as I mentioned, all interaction between the platform and the embedded controller, which is not something that would be viable in any way, shape, or form. But that's going to be something that will be added down the road, assuming that this ends up working out. Is there any more that I need to deal with here? No, apparently not. Okay, so Coreboot.config, thing system. Okay. Right, now how do I actually build this thing? Things I should probably check beforehand. Okay, let's get rid of a bunch of these windows. As you may have noticed, I never really got the memo about tiling window managers. That's on firmware. Let's go away. What could possibly go wrong? Oh, okay, just using package manager. Could be worse. Sure, go for it. Go absolutely wild. Okay, this may take a moment, so I'm just going to wander off for a second. I will be right back. Okay, I am back and just waiting for this to finish downloading its random additional bits of code. So unfortunately, the device I have does not have any particularly convenient access to the flash chip broken out. The flash chip is extremely accessible, but it's also not an SOIC package. So a common way of handling cases where you've flashed the wrong firmware or broken firmware or firmware just doesn't work is to place a clip onto the outside of the chip and then reprogram the chip from with an external programmer. The framework unfortunately uses a lower profile package for its flash chip, and as a result, it's not straightforward to do that. So in an ideal world, this will go right the first time. There's literally no universe where that's going to happen. Would be nice. So that effectively means that in the event that this doesn't work on the first attempt, I'm probably going to have to solder a bunch of wires onto the motherboard, which is not ideal, but is probably achievable. So one of the really nice things about the framework is this is actually shipped with a tool that allows you to unscrew all the screws on the device and a little plastic spudger for you to prise the case open. So I do appreciate the extent to which they've gone to in order to make this a machine that is actually usable by an end user, even outside circumstances that they previously imagined it would be. So I'm just going to grab that so that I can pull this open and make sure that the flash is still where I thought it was. Yep, there is a nice flash chip sitting right there waiting for terrible things to happen to it. One of the cute details is that there's a small sticker inside that contains a list of the framework team and then a link to their careers site for people who are interested. I have to say that, you know, like I said, this is obviously a pre-production machine. It is not in the same state as the production boards. Honestly, I'm still a ThinkPad person, but this is entirely accessible hardware. I'm not feeling that there are any points of this which have been cheaped out on in any way. Should also go with, YouTube requires me to say this, that while Firmware did send me this board, there is no expectation that I'm going to keep it. I'm not being financially compensated in any other way for this work. And I'm in fact not being financially compensated at all. Oh, come on. Why is it the last 2% that takes all the time? So Firmware have demonstrated some degree of enthusiasm about open source firmware. When I say some amount, I mean massively more than the majority of hardware vendors do. The source code to the embedded controller is already on GitHub, can be modified. You can reflash different embedded controller firmware on there. This is not something that's unique to Framework. System 76 have firmware for their embedded controller available, as well as the Coreboot environment. And in the general case, Chromebooks and similar devices also have the embedded controller firmware available and are running something that's Coreboot derived. So I think the thing that's more interesting about this is that it's a machine that is explicitly designed to be repairable. It's designed to be as modular as is possible with modern technology. Obviously, we're no longer at a point where it's straightforward for someone to just completely independently rework the motherboard and produce a new one. That's not a super plausible task. But to the extent that it is something that can be competitive with modern technologies, with modern large vendor laptops, and still actually offer something different? I would say that it does seem to. Come on, I want to build some firmware and then flash it onto a laptop. Sorry, I should really have done this beforehand. My apologies. Okay, looking like we are through the worst of this. No, okay, we need to check out various EDK2 subcomponents. Still kind of horrifying that EDK2's default crypto implementation is OpenSSL. It's a lot more code than I really like being there. Okay, shortly I should actually be able to kick off a build, which may or may not succeed. It's actually kind of amazing to me how quickly the entire Coreboot image ends up building. It's sort of on the order of, it is frequently faster for me to build an image from scratch than it is for me to actually flash that image onto a system. It's kind of wild getting used to building things where, yeah, I expect a 30 megabyte binary, and where, well, Coreboot is in this case going to fit into a 32 megabyte. Oh, right, that's a point. Did I edit? Yes, no, that configuration was fine. I think. Let me make sure that I did actually update the SPI flash size for this board properly. I did. Okay, good. And also, apparently, I did my arithmetic correctly. Wait, they're using boring SSL as well? What? Carry fight? What? Why is there Kerberos in my firmware? No. So yeah, while in this case the firmware is going to end up in a 32 megabyte flash chip, the Coreboot component of that is going to be a lot smaller. Yeah, not really much else to say about that. Why is there so much crypto code here? Maybe some of our life choices were bad as a society. Okay, that's looking more promising. Installing Rust. Rust is installed now. Great. Context here is that System76 have built various components of their firmware runtime in Rust, which, as far as I'm concerned, is wonderful. The more stuff that is not written in C that's running in a privileged environment, the better. But it does mean that as a result, it's having to download an entirely additional toolchain to do this, which will take a little while. Amazing. Okay. What? 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 No. No, that's not what I wanted to happen. Okay, at which point here did I screw up? Oh, right, I was supposed to... There we go. I guess that's doing something. That is definitely doing something. The first thing it's doing is downloading everything again. Well, not everything. I had no idea that people would be willing to just sit here watching package managers download stuff. The future's an amazing place. Anyway, lesson learned. Next time I should actually just do everything before streaming it and then avoid all of this. But sorry, I was not aware that it was going to end up downloading quite as much as it's ended up doing. Yeah, I mean, so YouTube's, I think, not particularly enthusiastic about the fact that I'm sending it a 3440 by 1440, no, 30, yeah. I have a hipster monitor, there's a lot of pixels, and I don't know that YouTube's super happy about getting all of them. Also, I'm trying to encode H.264 on the fly with CPU while also using the CPU to build this. This is probably one of those scenarios where the correct thing for me to be doing would be plugging the video output of the machine where I'm doing this work into something else that would be doing the streaming instead. But it's not that I don't have enough computers. I have a lot of computers, but my wiring setup is not sufficient for that to work. Although having said that, there's only, I think, 1, 2, 3, 4, 2. Yeah, there's only 5 computers on my desk at the moment. Once we're done with this, I will go back to streaming my attempts to coerce Amiga Unix into supporting my weird FPGA-based graphics card. Oh, we're building some things now. I had not realized that System76 had built their own SMM store implementation. That's nice. And in Rust. That's amazing. So for context, generally the system flash on a PC platform is configured such that it's not arbitrarily writable after the system has booted. The chipset will only permit you to write to the flash if you are currently in system management mode, where system management mode is a magical CPU feature where if you do something where the system is configured then it will you do this thing, and then suddenly the CPU stops executing. The operating system starts executing some code from the firmware instead. And that's used for things like secure boot, because you want to avoid it being possible for the operating system to just rewrite the secure boot key database, because if it could, then someone who gains the ability to subvert the operating system could basically subvert the entire secure boot implementation. So instead, the Flash controller is configured such that it will only allow writes to Flash if they're in system management mode. But if you're going to protect the EFI secure boot key database data, you still need the ability to update that at runtime in order to revoke signatures, revoke keys if they should be revoked, to add new ones if they should be added. And that means you need the ability to still perform writes. And this is handled by so-called authenticated variable updates. The variable update has to have a signature on it. When you try to perform the write, you make a specific UEFI call to do that. The CPU stops executing the operating system and instead starts executing code from the firmware in order to verify the signature on the update, and then updates the flash if and only if that signature is valid. Most implementations of system management mode are doing all of this in C, and so you've got a whole bunch of signature validation code in C in firmware running in an environment that is actually more privileged than the kernel, and which can be triggered from userland. So rewriting that code in Rust instead of C seems like an astonishingly good plan, because that is likely to reduce the attack surface significantly. Rust doesn't prevent logic errors, but it is designed in such a way that it's quite difficult to accidentally end up producing code that will execute arbitrary code in response to someone feeding it deliberately malformed input. So I am extremely happy to see the SMM store implementation, the component of Coreboot that is responsible for performing the update. Well, Coreboot EDK, one of those, that's responsible for validating that input and then only performing the flash update if it's legit, be written in Rust instead of C. That's kudos to System76 for doing that work. So we are now building the EDK2 payload, the EFI payload that will, if everything works, be launched by Coreboot when Coreboot has successfully initialized the hardware. Okay, so it built EDK2, now it needs to download a toolchain so that it can build Coreboot itself. So you may remember earlier I mentioned that something that was complicated is that we don't know how to write code that initializes the memory controller, and we instead rely on binary code that's provided by Intel for that purpose. This leads to a sort of interesting chicken and egg problem. How do you deal with a scenario where it is sufficiently complicated to access RAM on a system that you feel that that is proprietary value add that needs to be embodied in proprietary code, and which is then complicated for people to reverse engineer, and actually execute that when you have no RAM. x86 does not have a lot of registers, even in 64-bit implementations. If all the data you're trying to store while you're bringing up the memory controller, while you're training the link between the memory controller and the RAM, is if you don't have the ability to stash any of that anywhere other than in registers, you're going to have an incredibly difficult time. And so the way this is handled is basically modern CPUs have quite a lot of RAM on the CPU, and they make use of that for this purpose. You have a lot of cache, and the cache is used to basically, you can set the CPU up such that the cache is tagged in a way where if you attempt to access memory, you instead access the cache, and then accesses to the cache work even if there's no physical RAM backing them. So you're able to set the CPU up in such a way that you're able to pretend that you have RAM even though you haven't brought up the memory controller yet, even though you're not able to talk to the RAM that's in the DIMM slots. So apparently I'm running out of disk space. Let me just try to delete a couple of things quickly. Okay, that's better. So this is referred to as the cache as RAM, or CAR, stage of Coreboot. So initially, Coreboot, when the CPU comes up, the flash chip is mapped into address space as if it were memory, and you start executing code out of flash as if it were memory. At that point, there is no memory, so the only way you can store data, the only way you can pass data between calls is by putting them in registers in the CPU and doing so. So initially, we start up in 16-bit mode, we program the CPU into more useful space, we set it up so that the cache on the CPU can be used as if it were RAM, and then we have the ability to execute a bunch of code that will be, that needs to store temporary data until we finally get to the point where we have functioning RAM. We are way, way past the point where you apply power and your hardware just starts working, unfortunately. So I think this evening my plan is going to be attempt to get a Coreboot build, flash it, and then if it doesn't work, or if it does work, we'll probably end there, because you're not going to want to watch me repeatedly fail to solder wires onto a board. I'm really, really bad at this. It's going to take me a while. So something also to mention is that when we, so the system firmware, the memory training that I referenced earlier, information about how to configure the memory controller is stored in Flash by the code that does that. And that means that if you reflash the firmware, you invalidate that cache data, or you lose it entirely. And so it needs to relearn how to train the memory controller so that it can speak to the RAM correctly. This means that every time you flash a new Coreboot image, if you reflash the entire firmware in the process, you generally expect it to just sit there for a minute or so with no output occurring until it finally gets to the point where the memory is working and it will draw something on the screen, which is kind of, you end up sitting there for an extended amount of time, not sure whether or not the system is actually going to start working or not. It's surprisingly tense. Once it's built bin utils, it's then going to need to build GCC or... Yeah, sorry, the stuff I mentioned earlier about building Coreboot from scratch was sort of based on assuming you actually have the local toolchain configured first, which I did not in this case. Yeah, this is going to take a little bit longer. The irony of spending a bunch of CPU showing something building, taking away the CPU from building that thing. But once it's built a C compiler, we ought to be in business. I think this should be the last bit of infrastructure that needs to be built, and then it will go ahead and build the actual Coreboot implementation. The reason it's doing this is that Coreboot is really a 32-bit code base, and I'm running on a 64-bit machine, and so it needs a GCC that it knows is able to target the correct 32-bit code generation. In theory, the host GCC should be able to do this. In practice, when you're relying on a compiler to deal with hardware to the extent that we are in this case, the Coreboot needs to be extremely intimately familiar with the hardware in a way that most C code bases do not need to be. You really want to verify that the toolchain that you're using is going to build code that is absolutely correct. And that is sufficient to justify building a local toolchain rather than relying on the host one, because that could be using a compiled version that you have not tested at all. With luck, almost there. Really not speedrunning C compiler compilation here, I'm afraid. It would be kind of amazing to be able to just glitch through a wall and have a fully functional toolchain. Oh. And there's a whole lot of compilation occurring. This progress is definitely being made. Okay, GCC is built, and we should now be waiting to build an assembler. This should take much less time. Should. Looking promising. IASL is the Intel ACPI source language implementation. It is what takes the ACPI source language files and compiles them into a bytecode that will then be embedded in the firmware and later interpreted by the operating system. Spectacular. We are okay, downloading some more stuff. Close now. Meaningful progress is being made. So at this point, we're just grabbing a bunch of binary data that's going to be incorporated. Things like the microcode, stuff that runs on the CPU that is used for... the CPUs these days do not execute the instructions that they assert that they execute for the most part. Instead, there's a translation layer that occurs before that. The microcode is the layer on the CPU that is responsible for managing that. And the microcode that ships on the CPU is not necessarily guaranteed to work correctly under all circumstances. Updates may improve system stability. They may avoid cases where the CPU basically makes a mistake and does the wrong thing. But it's also an important part of adding additional functionality to work around security vulnerabilities. The majority of the Spectre and Meltdown type vulnerabilities, dealing with those involves running updated microcode. And as a result, we need to be able to ship updated versions of it that can be built into the firmware. Linux is capable of loading new CPU microcodes at runtime, but other operating systems are not necessarily capable of doing that, which as a result means that we have this, let's grab the latest stuff and put it in the firmware. We are now building Coreboot. Well, let's see whether this succeeds. Okay, that failed, but I suspect I know why. So I'm going to shift to the yes, what has happened here is that let me look at LSPCI again. Nope, that's the wrong computer. Okay, it looks like I was confused about where the 0 indexing and the 1 indexing occurs. I need to set those like that, and then 0, 1, 2, and 3, and then lose port 4. Okay. Right, running this again. So the issue there was that I had cut and paste something which duplicated values that should not be duplicated. The clock source usage stuff is almost certainly not correct, but again, I think that's something that can be cleaned up once we verify that we can actually get to the point of initializing the platform in the first place. So I'm going to treat that as a secondary requirement rather than a primary one. I said, what I'm doing right now is basically attempting to be the bare minimum for make Coreboot successfully initialize the hardware, not successfully initialize it into the state that we want it to be in. I think yep, another error scrolled past there. Different one though. PCIe RP0 doesn't, what? Is this a situation where Linux Coreboot and the FSP all have mutually, anyway, whatever. The framework that I'm using, there was a DIM in it when it was shipped to me. I did not choose that myself. The SSD in there is a, let me take a look. The SSD in there is one that I pulled out of my primary laptop because it suddenly started dropping off the bus. So it should not necessarily be considered trustworthy. It's an ADATA. Okay, I'm going to go with you did not build successfully, did you? Oh. Okay, so the build failure that was occurring earlier was down to the configuration telling the build system to incorporate a specific file as the microcode update. And that file was in fact a reference to the Git large file store artifact system. And because I just copied the directory without paying attention to the way the metadata is stored, it was attempting to interpret a literal text file, which contained a reference to the object it should be incorporating as the object it should be incorporating. So that is, unsurprisingly, it should not segfault in that case, but the easiest way around that was to just disable trying to incorporate that file in the first place. So the situation I have now is that while I flashed new content, it then tried to read back what had been written and discovers that it didn't match. There's data in Flash that is not what it wrote there. With luck, that's the management engine or something having decided to store some stuff there. It's probably, it's telling me very explicitly, do not reboot or power off, but Flash ROM is not the boss of me. So Solid's expectation is that the system will do nothing for a minute or so at this point because it's going to need to retrain the flash memory, the memory controller RAM link entirely. But it's also possible that it will fail to do anything because I have just completely destroyed everything that this machine holds dear. So we're going to wait a minute or so. Maybe something will happen. Alternatively, maybe this machine will be stuck on a black screen. If it is stuck on a black screen, then that indicates that I've got something wrong, but I'm not going to be able to recover that without pulling machine apart, soldering some wires onto the flash, and then being able to diagnose it that way. Coreboot has support for basically writing a log file into Flash as its the fan's running quite hard. That's not a great sign. Coreboot supports putting diagnostic boot logs into Flash, which, if you're able to write to the Flash, you can then read it out again, so you can extract those logs. Yeah, strong suspicion in this case is that the machine is not happy at all. So I am probably going to need to break it apart, attach some cabling to it, attach a flash controller to it, and then do a build where the logging data ends up stored in Flash so that I can extract it later and ideally figure out how far it's getting before it stops working. Give it another minute or so, but going to go with I'm not optimistic right now. At this point, really, any number of things could have gone wrong, so it's hard for me to even really guess why this isn't doing anything. Yeah, I'm calling it. This machine is not alive. Okay. Well, we have established that I am completely capable of generating a Coreboot build that will not boot a computer. And now you can too. I'm going to attempt to do some hardware modification to this so that I can extract data from it, and then we'll go from there and at some later point figure out, ideally, what went wrong and how to get back into a functioning state and how to update this source port so that it actually works. But I think we will end things for tonight here. Thanks everyone. I will let you know what progress is made.